Good morning, students. Can you hear me?
Good morning, sir.
Very good morning to you. People are joining slowly. Let us wait for 1 minute. Please switch on your videos just for because I have started my recording. So just attendance as a part of attendance, and also it is getting recorded also. So just switch on your videos so that you are available. Everyone to please switch on videos. Some people have switched on, but not everyone. Okay, I can see Pranav, I can see Manoj Kumar, uh, Purna Chandra, I can see, and I can see Amruta, uh, one more student, Pranav Pranav Sinha. Yeah. Sanjay, yeah. Hi Sanjay. Anushka, Anusha. Then we have Nagesh. Nagesh seemed to be like just finished puja. Very nice. Nice to see you.
Thank you, sir. Thank you.
Okay, great. Because generally we don't interact, so in the class we don't know who are the students. And other students, they don't want to show faces. Okay, you guys can switch off so that others can switch on so that they can come into the limelight. Others, please continue switching on your videos. By the time everyone joins, then I can start the class in another 1 minute. Beena, I can see Beena also. Hi Beena, good morning.
Good morning, sir.
And I can see Rakshit. Yeah, hi Rakshit. Nice to meet you.
Morning, sir.
Yeah, Mahima. Good morning,
Good
Mahima.
morning, sir.
Good morning. Good morning. So our students are also joining, like number of as the number of cases are increasing. Slowly the cases are increasing. Slowly people are also joining. So now it's almost 39. Yeah. Okay. I think we should start now. So I'll be picking up attendance any moment, anytime during the class. Okay. Can you hear me loud and clear? Once again, I'm confirming before the start of class.
Yes, sir. Strength is 5, sir.
Oh, shabash. Very nice. Thank you so much. So today we'll be covering, anyway, I'll start with greetings. Once again, good morning to all of the students. Uh, Today's class, we will see very important thing because some of the important terminologies, like we have a standing wave ratio and VSWR. Then we'll be discussing about the Smith chart, then single stub matching. Today in both the sessions, we'll be able to complete this. Along with, if I get some time, I'll be covering a little bit on the IAF, Indian Air Force life, and how exactly is this, a little bit I may cover. So more or less, these two sessions are very important for you because if you do not understand these techniques, terminologies, standing wave ratio, VSWR, Smith chart, and single stub matching, it will be very difficult if you can't. It's very difficult to self study, do the self study, and understand until somebody tells you or teaches you. It's really difficult. So I have made certain, because it's showing a Smith chart, how the calculation is done. So that is very difficult. But so I made one video so that you can understand very clearly, because the Smith charts available in the college, they are not, they are there, so but they are in the red color, but I have taken some other Smith chart, so which is little clear, so that I have now. Yeah. Coming to standing wave ratio, VSWR, Smith chart, we'll see one by one. So first of all, we'll see the standing wave ratio and VSWR. So what is a standing wave or a standing wave ratio or voltage standing wave ratio? So this is very important, you should understand. Whenever we have a source and a transmission line means a channel where you are trying to send the signal through over a media. And you have a load at the end. Load may be anything, you all know. So we have discussed in the last class also, whenever we have any mismatch in the load with respect to transmission line or the source or the characteristics impedance or the load impedance, whatever may be the mismatch, what happens is there is a wave. The wave actually supposed to be going out of the transmission line, but it will reflect back, where that is the one of the undesired signal which is coming back, which we want like no, my wave should travel forward. That means what happens is, if I consider an example, if I have a antenna connected to a transmitter, that means, like say example, any kind of transmitter for that matter, maybe your FM transmitter, let us say FM, you are hearing that songs, FM songs, right? Now you are having all your receivers. Receivers means you are all mobile. You can connect a earphone to the mobile and which acts as an antenna, and you can hear the songs and all FM 93.3 or 98.3, 94.3 or whatever the frequency. Now these frequencies are transmitted by the transmitter in the city somewhere. Now this FM transmitter has got a transmitter, a source, what is called as generation, where the signal like the songs are modulated, and then they are actually transmitted over a transmission line to the antenna. So antenna is there. So once it is transmitted from the antenna, the waves actually travel. So it is now within that range, 100 kilometers or 90 kilometers, wherever you go, you catch the signal and you decode it and you hear the songs, whatever the signal is being processed. Now, in case, let us assume in the FM transmitter end where the songs are being played, RJ and all, everyone is available and they are trying to throw the songs in the air. In case, if the antenna is not matched with the transmission line, that means the whatever the songs being played and they are being modulated and they are sent over the channel. Now, if that is not reaching, the antenna is near to that place only, maybe outside the building, within the building, the songs are being processed and they are being transmitted over a transmission line. The transmission line goes out of the building where the antenna is placed, just like your dish antenna. So now from there, the waves get out. Now, in case the antenna which is there outside is not connected properly or not matched technically, the load impedance, characteristics impedance. So what happens is you cannot transmit the wave properly. That means the songs which are trying to send to the air, you have, let us say that range of the FM signal normally is 100 kilometers, 100 to 120, you can outgoing way, you can pick up at around 100, 120 kilometers you can pick up. But incoming, while incoming, it will be less, range is less always. So now what happens is when you're trying to transmit for 100 kilometers, let us say average 100 kilometers of range. Now what happens if the full wave gets transmitted out from the antenna and you have fully matched load, characteristics impedance, load impedance, everything is matched, then the whole wave will go out. So 100% transmission is there. When you have 100% transmission, then you will have 100% results. That means you will, at 100 kilometers also, you can able to hear the songs on FM channel. Though there may be some disruption, but you can able to hear clearly the songs and all. Now the moment what happens in case the antenna is not, the load impedance is not matched with the characteristics impedance or the transmission line. So what happens is your wave, instead of going out 100%, it will be only transmitted some around 70%. 30% of the wave will get reflected. Now, please understand, out of 100, 70% is it trying to, the wave is trying to move out. Okay, please understand this, very important. 100% within 100%, 70% of the wave is trying to go out, but because of the some mismatch, not like full, but little bit mismatch is there. Now 30% of the wave is trying to come back. Now in the bargain, what happens? Your wave, actual wave traveled is 70 minus 30. 70 is trying to go out, 30 is coming back. So with that, what happens? Your actual result will be somewhere around 40%. That means your actual range will be within 40 kilometers. Like say, I am comparing with 100 kilometers with 100% your power transmission. So what happens is you will be able to listen up to 40 to 45 kilometers only. That means it will not go to the range of 100 kilometers. Your FM station within Bangalore city will be confined to the Bangalore city. Now, if you see at present, if you go to Tumkur also, you can able to pick up the FM Bangalore city FM signals. And if you go to even the outskirts of the city, around 100 kilometers from here, go towards Mysore also, but Mysore also has got FM. So there is a mix up of the signal. But however, if you go towards other side, you will get all FM channels coming up to 100 kilometers. So that means what? Your wave has to travel 100% outside. Now, because of some mismatch, your antenna is not matched properly with the transmission line, or even your maybe source may be not matched with the transmission line. There may be mismatch with the characteristics impedance of the transmission line with respect to the load of the transmission line. Any mismatch in the transmission line, for that matter, even some extent your source power, signal power, sometimes it may happen your transmission is matched properly, everything is matched 100%, but your source itself is having problem, it is unable to transmit that much power which is required. So there also you'll have all these factors, but standing wave will occur only in case of mismatch in the transmission line with respect to load. So if the source is like sometimes source may not be able to generate properly, but your transmission line is matched, then what happens? The wave will not have any, we will not have any kind of a standing wave in the, but power will be less, but signal power will be less, but however, it will transmit 100%, whatever getting from the source, because source itself is transmitting less. So the antenna is also transmitting whatever the source. So this means what? The standing waves will occur. The standing wave means a wave, you can see this slide. Now this is one wave, which is the original wave, the wave which is trying to go out, the blue color line, which is trying to go out. Now there is a reflection wave also, like lesser than the original wave. Let us say 30% of the wave is trying to come back. Now because of this 30% wave coming back, their results, because we will be having a forward wave and also we will be having a reflected wave. So what happens is there will be a standing wave pattern. So the wave, some of the portion of the wave is trying to come back, so which forms a part of the standing wave. In case of oscilloscope, you must have seen some some kind of spurious signals coming in between during doing experiments, like in the your transistor and other parameters. You are doing some kind of experiment. So that time you suddenly see because wave is trying to move out to the this thing, but there is a standing wave. That pattern can be seen sometimes in the oscilloscope also. That may be not because of transmission line, because of some other parameters, but that can be seen as a, like you can see the signals, like how. So this is the way I can show you. This is the standing wave. Like this is you can see the forward wave, and you can see some reflected wave also coming back. So with that, now there is a wave is in. That means what I want to compare with this is you are trying to send water in a pipeline. If the water flows out continuously without any problem, then nothing will happen. But if you try to stop the water at the some portion of the water is you try to hold it at the end of the water pipe, what happens? The water will get stagnated. That means the water will stand there only. It will not go out. Some portion may go, but some that is have a standing wave, water wave, so something like that. So it is similar to that, just to understand things. Now this here I have shown a Smith chart also. You can see this is the Smith chart, which looks like I will be explaining clearly now. Can you see? Can you hear my voice, students? Confirm, please.
Yes, sir.
Yes, sir. Yes, sir.
Okay, fantastic. Okay. Okay. Now I'll be covering from different things so that the life is easy for you, so that you can score maximum marks in the exam. I have downloaded certain things from some material from your notes, college notes. We have nicely college made notes. So that also I have taken and some data I have taken from outsourced from the internet also, and some data which I have collected from my Air Force data is also there. So everything I have made it, and I have compared with the question papers. So what is the best suited for you is, if you study this, you'll be able to clear all exams with flying colors. Okay, with that motive, so we'll start with the voltage standing wave ratio. You understand now what is standing wave. Standing wave is defined as a ratio of the maximum, in case of voltage standing wave we're talking about. So it is a ratio of the maximum voltage to the minimum voltage of standing wave is shown in the figure. Now we have a VSWR, that is voltage standing wave ratio, is called as, because we call it as a ratio because we have both forward wave and reflected wave. So we call it as a ratio, and it is expressed in VSWR, like, voltage max by voltage minimum. So the V max by V minimum is your VSWR, voltage standing wave. So that means in a wave, this is like consider this wave as a standing wave. We saw that this is a wave, total wave I'm talking about. I'm not talking about incident wave or reflected wave. Total, if I take both the waves, I'll have a resultant wave, which is in the channel or the transmission line. So this is from the generator side and this is from the load. If we have this wave, standing wave, in that whatever is the maximum peak, V max, and also we have V minimum. Now, why this V max and V min, why we have kind of a sinusoidal wave? That is also a big interesting topic, because see here what is happening is the wave is trying to move out, and the wave also is coming back, reflected wave. Because we consider the standing wave means there is a forward wave and there is a reflected wave also. Now, when we have both the waves, now what happens is the forward wave which is there, the reflected wave, sometimes it may exactly come back, or it may be little offset, maybe a 30-degree offset the direction. We are talking about direction of the wave. It may not exactly come back straight. So it may be, sometimes it is in phase, sometimes it is out of phase. So it happens both ways. So when it is in phase, the voltages get added up. So we will have a positive peak. And sometimes the reflected voltage is out of phase. That means the voltage is out of phase, means we'll have a combined effect of negative this thing. So we'll have a negative peak. So this will result in positive and negative peaks of the standing wave. So in that, if I consider the V max, that is the maximum voltage of the standing wave, and V minimum, the minimum voltage of the standing wave, if I consider both, then I will have that voltage standing wave ratio formula as V max by V minimum. So if I take the ratio of this, that will give you standing wave. So standing wave, superposition of incident or reflected voltages. That is, if I represent in the equation, V max is equal to, we know, we have already done in the last class, V plus e to the power of minus gamma t plus V minus e to the power of gamma t. This is one equation. And then we have a V minimum, nothing. V max is just positive, and so V minimum is your, see, this is your forward wave, and this is your reflected wave, something like that. So you, in the V max, you are adding up, and V minimum, you are taking the difference. So simple. So if you take the, as per the formula, if you substitute this, so you will have this formula. Once you do some calculation, you divide throughout by this term. So what will happen? 1 plus this whole term will become like this. So we know this is represented by gamma. So 1 plus gamma by 1 minus gamma. So this is your VSWR, simple formula. So if you put in this thing, VSWR minimum is equal to 1 plus gamma by 1 minus gamma, which is where you can say equate it to 0 minimum. Then what an ideal value of VSWR should be 1. Why? Now I have one small question in this. Whether this VSWR is desirable or undesirable. We want it or we do not want it. I have one small question here. I just wanted to see the assimilation of students.
So the value should be minimum, sir.
No, I am asking simple question. Value. I am not asking value. I am asking whether VSWR should be there in the transmission line or
shouldn't be there, I think.
Absolutely. It shouldn't be there. If you have VSW standing waves there, that means you are unable to transmit. There is a loss. It's a loss actually. Please understand, there is a loss. Always there is a loss if we have a standing wave. But what happens is the standing wave itself in the transmission line will create like a lot of other issues. But what happens in practical? Theoretically, we say that 100% it shouldn't be there. But practically when you put, there will be a small mismatch always. You will never have 100% transmission line transmitting with the proper matching and all is not possible. So there will be a small amount of mismatch somewhere in the transmission line because of the length of the transmission line and the frequencies involved. So there may be definitely there will be a transmission line, but that should be within the limits. So that means what I want to say is there will be a small amount of transmission line always there in your signal. That is there. So that is what I basically wanted to conclude. Yeah. So now my ideal value of the VSWR should be 1. And from it actually ranges from 1 to infinity. Value of VSWR ranges from 1 to infinity. If the VSWR value reduces below 1, means your experiment is not correct. When you are doing some kind of experiments here in the lab, in advanced communication lab, you will find sometimes I have seen students getting values VSWR less than 1. So that means the experiment is not correct. You have to have experiments where VSWR values should be at least 1, preferably 1 or little bit more than 1. So now this thing, you can see the transmission line. I'll just flash it. Yeah, I can see that, otherwise it's very small. Yeah. This VSWR minimum is equal to 1. Therefore, for a perfectly matched transmission line, ZL is equal to Z0. That means we have that your load impedance is equal to characteristics impedance. Then we have a unity VSWR. So that's why this in the Smith chart, when we talk about Smith chart, there is something called as a unity circle, which is called as a reference circle. We'll be discussing that. Now, in the Smith chart, we have, now what is Smith chart? So we'll be discussing about the Smith chart also, because it is all, they are all related. VSWR, Smith chart, single stub matching, and all, they are all related. Okay, so that's why. Now there is something called Smith chart. Now what is the Smith chart? Smith chart is basically a graphical tool, basically a calculation tool, which is used to find the transmission line properties. Like you have reflection coefficient. Already we have done some calculation using formulas. Reflection coefficient. We know reflection coefficient of a transmission line is given by gamma is equal to ZL minus Z0 by ZL plus Z0, which is your characteristics impedance and all. In terms of this thing gamma and theta, you can see magnitude of this thing and direction. Here, the reflection coefficient will always have the magnitude and direction. Now, why the direction is there? Can anyone tell? Why this term, in the reflection coefficient, we have the magnitude and also the direction, the theta. Why this is there? Because the reflected wave may not be exactly reflected back. It may be little offset from the actual original the path, direction of the path. So it is not possible to exactly get back the reflections. It may be little offset also. So depending on how much it is offset, so that we need to calculate in the reflection coefficient. That means the reflection coefficient always be indicated by magnitude and direction, because how much it is getting reflected and what direction it is getting reflected. So that's why we do represent this reflection coefficient with respect to magnitude and direction. So that means the reflection coefficient is a vector quantity. Then we have VSWR. VSWR, we know voltage standing wave. That is a wave which voltage is supposed to go out, but the voltage is coming back. So which is causing a standing wave pattern. That is called as voltage standing wave ratio, which is called ratio because we take ratio of voltage maximum to the voltage minimum. So that is given by this. Then we have, it is also used to measure VSWR, Smith chart. Because what happens is, in some calculations, it is easy to calculate the VSWR by formulas and all. But sometimes it becomes really, for the complex transmission lines, microwave complex transmission lines, it becomes really difficult to actually calculate VSWR by calculation. That time what happens, the Smith chart is used for calculation. That means using Smith chart, it is really easy compared to doing equations. There are some graphical tool, so you have to do some kind of line drawing, drawing circles, taking this thing values and all. If you do that, it will be able to calculate that using the Smith chart easily compared to other things. So by mathematical models. Now then we have something called single step matching. Now single step matching technique also can be measured by also can be done by the Smith chart. Now we'll discuss in the later slides what exactly is the single step matching and why it is required and all. Okay. So with that, we move forward to the next slide. I will be showing like one small video which made by our team only. So it explains the standing waves in terms of voltage and current, and actually it will show you exactly how the standing wave occurs and how can we understand the standing waves. Okay, I am playing the video. In case any problem, kindly let me know. Can you hear the sound? Please put up your
Not
earphone.
clearly, sir.
Sorry?
The sound is not very clear, sir. Like,
Yeah, it is not very clear. There is some issue here.
yeah.
1 second, I'll try to increase the volume of the video. Try to, because there is some. Because whatever best possible we try to do, but what happens is sometimes no video, our video is good. Now see the, yeah, I'm increasing the strength. Let me see now. So with this, what happens is sometimes no, you get.
In this video, I am going to explain standing wave.
I have increased the volume.
How standing wave
Now it is okay.
how to calculate
No, sir. We are not able to hear that volume of the video clearly.
Yeah, please bear with this. This is the best I can record because I can't have any other source for this more than that. You put either earphone or something, try to concentrate.
V1 into e to the power
I have increased the maximum the volume.
this length of transmission line is considered as L. So ultimately, incident signal that will be V1 into e to the power minus 1L. And
This is your incident signal. This is the transmission line. I'll be explaining. Don't worry. This is the load impedance. This is the reflected signal. We all know incident signal V1 e to the power of minus gamma.
signal is getting incident. That is having effect of reflected signal. So ultimately, if we measure line impedance in between this transmission line, so that is getting changed because of reflection. So resultant signal which we measure in between transmission line is depending on what is the phase of incident signal, what is the phase of reflected signal.
See, phases are also considered here. Very important.
Signal is out of phase, so at that time voltage is getting subtracted, and sometimes signal is in phase, so voltage is getting added.
As per the phase, the signal is getting added and subtracted.
There will be addition of voltage and subtraction of voltage. So with respect to position,
when we consider with respect to position,
voltage,
how the voltages get added and ultimately how voltages bifurcated. So that will be see. Now we can see here the voltage.
At this instant, there is Vmax. Because of voltage is getting added, voltage is input. And at this instant, there is Vmin, and that is happening because of out of phase voltage.
Here is Vmax because of both the signals getting added up, and it's in phase. This is in phase and this is out of phase. So V minimum, the difference in the signal.
Vmax that happens in case of V1 and V2 addition, and Vmin that happens in case of V1 and V2 subtraction.
And this is your length of the transmission signal L.
If I say V1, that is
Now see these equations. We say one forward wave and reflected wave.
that happens in case of V1 plus V2 in phase voltage addition, and Vmin that happens in case of
This is your Vmax is V1 plus V2. Both the voltages are added. Now V minimum is both the voltages are there is a difference in the voltage.
V2 by V1. And if I take V1 common from this, so that is resulting into 1 minus V2 by.
Just take common V1 like this. You will have this equation.
Is a ratio of maxima to minimum.
Now we know the standing wave, that is VSWR, is given by V max by V minimum. So you divide both the equations.
That is V1 into 1 plus V2 by V1 divided by V1, that is V1 into 1 minus V2 by V1.
Both will cancel.
I will cancel. This will be 1 plus V2 by V1 divided by 1 minus V2 by V1. And V2 by V1, that is the reflection coefficient. The reason is V2 is reflected voltage, V1 is incident voltage. So we can say VSWR is 1 plus mode of rho divided by 1 minus mode of rho. So this is VSWR.
So this is given by 1 plus mode of rho and mode of 1 minus mode of rho. So this is the final equation of the VSWR.
With respect to 1 plus mode of rho divided by 1 minus mode of rho. Now, if we talk about what should be the range of VSWR, then we know reflection coefficient that belongs to 0 to 1. So we need.
Saurabh, can you hear me? I hope my connection is okay.
Yes, sir, your connection is okay. We can hear you.
Okay, fine. I'll be explaining in between also, because the audio I'm trying to get the maximum best audio, but sometimes there is a problem, because in the recording we have this issue. No, see, understand this is very important. Once you have the VSWR is equal to 1 plus modulus rho by 1 minus rho, we have the value of the rho varying from 0 to 1. When we have 0, VSWR value will become, this is VSWR, 1 to infinity. That means whenever we have the reflection coefficient ranging from 0 to 1, my VSWR changes from 1 to infinity. That means anything value VSWR lesser than 1 is not correct. It has to be at least above 1. Minimum 1 for perfect matched transmission line, and it can be little more than that depending on your reflection. How much is the reflection coefficient?
The more things that we can understand, and those are what is the maximum impedance and what is the minimum. So maximum impedance that will happen in case of Vmax divided by Ia. And if we place values, in that case we can say this will be Z0 into VSWR.
See, this maximum impedance can be given by voltage maximum by I max minimum, which is given by, we know this formula. No? With that formula, if you equate the characteristics impedance into your VSWR. In case of minimum impedance, it becomes V minimum by I max. Z0 into, divided by, it will be divided here. See the difference.
Now we can have a calculation of maximum impedance. So
for maximum impedance, it is multiplied by VSWR, but for minimum, it is divided by.
maximum reflected voltage is V2 and minimum maximum incident voltage is V1. So V2 by V1, that will be the maximum value of reflection coefficient. Because of standing pattern is getting sensitive, there will be maximum, and maximum voltage could be addition of voltage because of in phase voltages which is there on transmission. The minimum voltage that happens because of out of phase voltage, so that is getting subtracted. So V1 minus V2, VSWR is Vmax by V, and that is result. So VSWR could be 1 plus mode of rho divided by 1 minus mode of rho. Reflection coefficient value that is there in the range of 0 to 1. VSWR value that is there from 1 to infinity. Thank you so much for watching this video. If you like this,
So we know about the standing wave. Any doubt in the standing wave? Anyone got any doubt? Mahima,
No, sir.
have you understood the concept?
Yes, sir, I've understood.
Have you
Sir.
understood the standing wave? So question will come in the exam. That is very important. What is a standing wave ratio? What you understand by standing wave ratio? What is VSWR? There will be some calculation also. Okay. If the calculation problem comes, if you given with characteristics impedance and VSWR and some parameters, you need to calculate the standing wave pattern. So all that thing will be there. Okay. Voltage max, voltage minimum. Use the formulas and calculate. It is simple. And also we will try to calculate the VSWR by Smith chart. First of all, we have to understand what is Smith chart. So Smith chart is a very important tool. Like Smith chart invented by Philip H. Smith and T. Mujohasi is a graphical calculator or a kind of a tool, graphical tool, or a nomogram, or I can say nomogram, designed for electrical and electronics engineers specializing in radio frequency engineering to assist in solving problems with the transmission lines and matching circuits. So these are the very important tool which is used for basically for the electronics and electrical engineers for matching, basically who are working in radio frequency engineering, microwave engineering and all. So they require these kind of tools. But we have never used in IAF the Smith charts, but probably in some areas it may require. So in the radio frequency calculations, it may require, because nowadays all new equipments are available, new systems are available to measure all your impedance, frequency, V max, V minimum, VSWR, everything you can measure by new methodology. But since it was a method which is there, you without using any systems, still you can go ahead with the Smith chart, because as an engineer, RF engineer or a radio frequency engineer, you should know use of Smith chart. So that is the reason it has been kept. So you understand how we can calculate. Once you know this, probably in your life you can use it or you may not use it, but you should be knowing the technique of using it. Since it is in our VTU syllabus and this will come in your exam, so it is important. So you have to study. So please concentrate. This is very important. And second point is that Smith chart can be used to simultaneously display multiple parameters, including impedances, admittances, reflection coefficients, scattering parameters, noise figure, circles, constant gain counters, and regions for unconditional stability, including mechanical vibration analysis. See the application of this Smith chart. Now here, whenever we having any kind of mechanical vibrations analysis we need to do, that means a condition where you want to calculate conditional, unconditional stability within the system, any system for that matter, maybe an engineering system, which may include mechanical, electronics, electrical system, a complex system where so much of complexity is there. So that times it is very, very difficult. It becomes very difficult to do the calculation by using normal mode of mathematical this thing. So that time these Smith charts are actually come into play. So this Smith chart will help you easily. You can calculate the what are the parameters required for this, what are the vibrations, everything you can calculate using this. So the Smith chart is most frequently used at or within the unity radius region. However, the remainder is still mathematically relevant, being used, for example, an oscillator design and a stability analysis. So this is there. So now, while the use of Smith chart paper charts for solving the complex mathematical problems, which involved in matching problems, which are replaced by software-based methods, the Smith charts display still the preferred method of displaying how RF parameters behave at one or more frequencies, an alternative using tabular information. So what I mean to say is that there are so many softwares available now. There are so many other systems available to calculate all the things. But this Smith chart also gives you accurate results. And because sometimes, what happens is if you have a Smith chart, if you are working in some kind of a situation where suddenly there is a, like you are working on a system, you are having all software based and hardware based systems for calculation of VSWR and all. Now what happens is there are certain research area where suddenly if something happens and if the power is not available or because of some other reason, short circuit or something happens and all, now at times you need to have a, immediately you have to do the calculation. That time Smith charts will pitch in. Now you have to keep Smith chart as a standby. You cannot say that in the research, like, some critical research is going on and suddenly something happens accidentally. If some calculations are being to be done on urgent basis, that time Smith charts will help you. Thus, most RF circuit analysis software includes a Smith chart option for the display of results, and but all but the simplest impedance measuring instruments can display measured results on a Smith chart display. So these are the small like Smith chart display. This is the circles are there, concentric circles are there, you can see, and there are some outward circles are there. We'll see how exactly and what are those signals, and there are certain lines on the bottom you can see, just like your scale, like that. No, so your protractor, it is a it's a combination of your protractor and scale and all other whatever you have. So some kind of a tool, but not exactly like protractor, but something related to that. We'll see how exactly this is in a video. I would like to show you. It is explained very nicely by our team, and see, I will tell you. I will show you the Smith chart video. Please go through. This is very important video. Next 20 minutes or so, it will be there. In between, I will be explaining also. Please kindly concentrate. I request everyone, each and everyone, please concentrate this. Once you understand this video, and I will be giving this video to you also, and in between, I will be explaining to you during the video session. So this is the Smith chart. Okay.
I'm going to explain Smith chart and how to solve examples of Smith chart. So here you can see this is a Smith chart where first we need to understand what is the meaning of this circle which is there in this Smith chart. So in this Smith chart there are basically two types of circles. One is you can observe these circles.
These are the circles.
So this circle,
concentric circles.
So that gives idea about the real value of impedance which is there with this Smith chart.
That is the real value of any impedance.
This circle.
There are circles which are here like
These are
half arc, imaginary circles.
So imaginary circles are having basically two categories: positive imaginary and negative.
The positive is upward. Upward is positive from this line.
Above this horizontal line.
All these lines are
Positive imaginary circles, that is above this horizontal line, and negative imaginary circles, that is below this horizontal line.
These are all a negative imaginary circle. These
So
lines.
this is how these circles are done. Now what are
So once again, I will explain here. Please concentrate. I have paused the video. See, these circles which are there, these concentric circles which are emerging out of from this point. See, it is emerging. The Smith chart has to be placed like this. You can see a group of circles like this. It will be right side, always on the right side of your this thing. So the circles are originating from here. You can see so many circles are originating, but you can see a prominent circles which are coming out like a wave. It is increasing circle order. You can see these circles are your, which indicates your real part of the impedance. Now there are circles originating from here and going like this, arc, just like arc. They are not full circles, but they are arc from here like this. They are originating like this. Now these circles actually gives you the impedance, which is the imaginary part of the impedance. Now there is a line, horizontal line like this. Anything above this, that is the line arcs. I will differentiate into circles and arcs so that to make it understand. These are the circles, which is a real part of the impedance. Now the arcs are there. So these all indicate the imaginary part. In that again, there are two things, arcs. Like say arcs are divided by 2. This is the horizontal line. Any arc ultimately above the line is a real, imaginary, which is positive imaginary portion. And anything which is below this line is a negative imaginary portion of the impedance. Everything clear? All students clear? Please acknowledge.
Yes, sir.
Any doubt in this?
Yes, sir.
No doubt?
No doubt, sir. It's clear, sir.
So shall I proceed? Hello? Okay. Fine. I will be continuing the video.
So in this Smith chart, at this position, we have value of Vmax and Zmax. And at this side, we have a value of Vmin and Z.
See, we have, this is V minimum point, Z minimum point, and that side we have V max and Z max. So this is your from one end to other. That means it is going from here to here. So you can see now it will be explained.
So when we solve microwave circuits, we have standing pattern. So that is what resulting into V max and V min. So V max, that is there on this side of the Smith chart. V min, that is there on this side. So V min and that lies over here, and V max and that lies over here. Now if we see lower part of this Smith chart, then in that here these are the scales which gives idea about what is the value of VSWR. It is first horizontal line that is giving idea about value of VSWR.
See, this line indicates on a horizontal scale VSWR value corresponding to your Smith chart position. You have to actually correlate with the Smith chart position. If you draw lines from there, you will be able to calculate the VSWR. We'll be explaining clearly how this can be done. Okay.
That is giving idea about value of reflection coefficient.
The third line indicates the reflection coefficient value. First line is VSWR. Third line is your reflection coefficient. The rest you don't bother about other parameters.
So this is how this Smith chart is there. Now, when we look impedance, then from load, sometimes we move towards generator, and sometimes from generator we move towards load. So when we move towards the generator from load, we need to move in clockwise direction. So this is what towards the generator. Before that we need to move it in clockwise. And when we move towards the load, at that time we need to move in anti-clockwise. So towards the load, we need to move in anti-clockwise. So
this is very important. Whenever we are moving from towards the generator from load, it is always clockwise, and whenever we are moving towards the load from the generator, it is always anti-clockwise. This you have to remember, very important.
we move from load, we need to move it towards the generator. And when we move from generator, we need to move towards the load. So towards the generator, we need to move in clockwise direction. So towards the load, we need to move it in anti-clockwise. Now to understand this, let us solve one basic problem so that we can have a proper idea like what is that which we need to do.
With this situation, basics of the Smith chart, we can solve one small problem. Now in this problem, we are trying to solve the single stub matching problem. Like what is for that we have to understand what is single stub matching. Sometimes in the complex circuitry transmission line, what happens is what happens is that we actually get problems while matching the transmission line. When it is not possible to match the transmission line with certain adequate results, then what happens? We have to you have to use some kind of single stub you have to use. Now that will be explained, but before that we will understand this problem first. How can we solve certain transmission line problems associated with this? How using Smith chart? How can we solve a problem like this? Now we have the transmission line here. With characteristics impedance of 50 ohms and length of the transmission line 0.1 lambda, and we have a ZL, that is a load impedance of 5 plus J25 ohms. So this is expressed in real and imaginary. So now we'll be trying to do calculate the other parameters on using the Smith chart. So we can do a lot of calculations here. You concentrate on this. How can we do a calculation using Smith chart? Once you understand this, it will be easy for you to do any kind of calculations in future. I hope I am there. My connection is okay, Saurav?
Yes, sir. Your connection is okay. We can hear you, sir.
Okay. Thank you. Thank you. Okay, I'm just proceeding with the video now.
Let us consider one problem. Now, say in this problem, we have characteristic impedance that is zero, load impedance that is that. The characteristic impedance is 50, load impedance is 5 plus 2. Length of transmission is 11. So by using this, there could be so many parameters which we can solve by using smooth chart. So let us solve those parameters and you can understand what is the use of this. So as it has been described in this problem, Z0 that is 51 and ZL that is 5 plus J25. So in Smith chart we need to plot impedance, but that should be normalized impedance. So normalized value of ZL, that is actual value of ZL divided by ZB. So 5 plus J25 divided by 50, so that will be 0.1 plus J 0.5.
See, we have to directly, we can't take the load impedance and characteristics impedance directly for normalized. We have to make it normalized impedance for plotting on the Smith chart. So there is a conversion. So in exam, the question will definitely come. There are so many questions I have seen Smith chart. So directly don't jump to conclusion and directly don't try to plot all the problem. Like, you have to normalize. You have to first consider the ZL and Z0 is the characteristics impedance. Normalize it using normalized impedance is called as ZL by Z0. You divide. So once you divide this by that, what will happen is this will be 0.1 plus 0.05 J. So once you have that, then you move on to the Smith chart.
So when we plot ZL value on the Smith chart, real part of that should be 0.1 and imaginary part that should be positive 0.5.
We know what is real part and what is the imaginary part. Real part is a point where all the concentric circles are the real and all the arc circles are the imaginary, and positive imaginary is on the top, negative imaginary is on the bottom. So that is what you have to go.
So here to plot that, you need to understand real part should be 0.1. So these are real circles. Now where this real circle is having 0.1 value, which is circle.
This is the 0.1 point.
And imaginary, positive imaginary circles are there.
Positive image, since the imaginary is positive.
0.5.
So 0.5 here.
That is this circle. So this is real 0.1 and
0.5 is here.
Positive 0.5 that is intersecting at this position.
This position it is intersecting.
So it intersects at this position. So we can say value of ZL
that is normalized impedance
at this point is 0.1 plus J 0.5. So that is how we can plot a point ZL on this map. Now, by using this point, we can have VSWR circle. So that will be a circle, which is what we need to plot with respect to.
See, basically understand here. Sorry. Here, in this position, you can understand there is here. It is 1, 1. This is the unity circle. What we talk about. This is the unity circle. I told VSWR should be 1. So this is the unity circle, the reference value. That's why we have to consider from here to that position. We have to consider, and we have to actually. Actually, I will be video. Okay, I will go because I have to forward this video. Okay, what I do, I will play from the source so that I can control my video easily. Ending with Smith charts. Smith chart. Okay. I can vary the video position.
In this session, that is 5 plus at this point.
So we were here somewhere here.
0.1.
Can you see the video now?
0.5.
Yes, sir.
Okay, fine.
Plot a point ZL on this mixture. Now, by using this point, we can have VSWR circle. So that will be a circle, which is what we need to plot with respect to.
This is your unity circle, VSWR point
So
1.
right now, we will be plotting VSWR circle. Now you can see center that is over here, and we are tracing circle with respect to this value. So this is what a circle which is VSWR circle. So you can say now this circle, which is what we have traced, that is VSWR circle. Now, to understand how to calculate VSWR, we need to consider a VSWR circle intersecting to horizontal line. The horizontal line is this. So here it intersects at this point.
It intersects here at this point, somewhere here.
At this point.
We have focused the camera also.
So we need to trace.
You have to use a scale
Horizontal straight
and draw a vertical line from there to down.
So now this line, which is what intersecting to horizontal line by VSWR circle, that is what we are stretching it to the scale.
Now we know this first line is VSWR value.
So here we can see this line intersecting over here to VSWR scale to this first line that over here. At this point, there is idea about what is the value of VSWR. Now, in this VSWR value that lies in between 10 to 20, and that is bisected by 5 points. So after one point, this scale is there. So we can say
12.
value of VSWR, that is 10 plus 1 point, and each point is having value of 2. So value of VSWR should be 12 approximately. And third scale, that is this
Reflection
which is
coefficient.
intersecting over here. So this scale explains you value of reflection coefficient. So that is that in between 0.8 and 0.9, and that is again bisecting by 5 points, and that is there after second. So it is there in between 0.8 and 0.9. So after the 2 points it is there. So value of reflection coefficient is 0.84.
See, it's 0.8 here. 4 points after this thing, so it will become 0.84.
We are in reflection coefficient for this transmission. Now, to understand some other parameters, what we can do is we can calculate input impedance.
Input impedance we can also
Problem,
calculate.
it is given length of transmission line is 0.1 lambda. So let us first of all plot a line which is what exactly is coming out from center to Z.
This is always considered as center.
This
1.
line, that is what coming out from center to Z. So now we can see this line is intersecting to angle over here. So what does that point indicate? This point indicates a value of reflection coefficient at Z. Now reflection coefficient, that is magnitude of reflection coefficient into e raised to j sin, where sin is what phase of reflection coefficient. So over here, angle is in between 130 and 120. Angle is in between 130 and 120. So it is there after 120. We can say this is almost 126. So value of reflection coefficient is 0.84 and angle is e to the power j 126 degree.
See, we have calculated the reflection coefficient magnitude by drawing the vertical line. Below, we saw it was 0.84 was your magnitude of the reflection coefficient. But we reflect every reflection coefficient, we along with the normal magnitude, we have the direction also. So the direction is calculated by using this technique. So this is the like e to the power of j 126 degrees is your 126 degrees is your the reflection coefficients with the reflection direction. So please understand, magnitude of both, it has got reflection coefficient, has got both magnitude and the direction. Okay, shall we stop here? You want to go for a break?
Yes, sir.
Or should we continue? Okay, let us have a break because I don't want to take your break. The break is always required because you are sitting since morning. So because I believe in breaks, because if you have break, you will get energized and come back with. But I want to pick up the attendance. Kindly hold on. Now I'll be picking up the attendance. Please don't go. Give me 30 seconds. People are leaving. Yeah, wait, again I'll take people join back. Wait, again I'll pick up the attendance once again. I'll save the data because 2 people were missing from the class. This is the HMTL. Again, I will do. Anyway, that will be there always. Okay, fine. Okay, you can take a break and come back at sharp at 11:30. Some interesting topics are for you. So please come back fast. Air Force, I'll be covering some parts of Air Force also after this video. So what are the benefits of Air Force and all I'll be covering. So better you come back. We'll have a 50% session so that I'll motivate and show you the importance of Air Force also. Okay. Okay. Have a break. Have a cup of tea and come back. Thank you.
Sir, can you please share the video, sir?
Of course. This is meant for you only. It will be shared after this class. I will. The first thing is I'll share the videos. Okay. Don't worry. It will be shared everywhere.
Thank you, sir.
Yeah. Sure.
Thank you, sir.
Yeah.
Thank you, sir.